I see that quite a number of people have signed up for Slack, so do me a favor and post in Slack what kind of field of science are you in and what is your favorite programming language. What is your science? What language do you program in? I prefer to use Slack for communication rather than Zoom chat because I can keep Slack on a different monitor and the Zoom Slack keeps popping up and my screen loses focus. It's very annoying. So petroleum engineering. So I assume partial differential equations are nothing new to you. Python and C. Okay, very good. So we need to get some logistics out of the way, and let me just, which of the many Slack channels? 2022 PETSc tutorial. At the moment there's only a couple of 2022 channels, so you'll easily find it. 2022-PETSc-tutorial. Okay, and let me start sharing my desktop. Plasma physics. Cool. I have no idea what that looks like once you get computational. Python C++, Python C++. Okay, interesting. So, Patrick, I see that you found the Slack channel. Very good. Okay, so the Slack channel has a couple of pinned items at the top. Let's see, you can see my desktop, I think, because I'm screen sharing. So I have a repository, parallel programming public, and so I have a window open on Frontera, and I have cloned that repository somewhere. So you need that repository for doing exercises. Parallel programming public, git pull. I am up to date apparently. Yeah, so here under the clone button you get git clone, and I think on Frontera you may need to clone with HTTPS transport. So clone that thing on Frontera so that you can do the exercises. That gives you a directory, parallel programming public, and then there is an exercises directory, so you go into exercises. This, by the way, has the whole source of my textbook, and then here you see that there are PETSc exercises in C, Fortran 2008, and Python. There's really no C++ interface to PETSc, sorry. Right, that's one, and the other link that is pinned is to this Corral TACU Texas EDU, so that is file storage. And let's see, you need the PETSc course.pdf. Unless you're going to be doing this in Python, then there's the PETSc P. So far, no one has said that Fortran is their main language. Okay, good. Okay, so I have one window on Frontera for the exercises. I have my web browser. So PETSc moved their website the other day. it is gratifying to see how many people are speaking C++ these days instead of C. I am really starting to prefer C++. Next week, I'm teaching a C++ for C programmers course, which will discuss some of the new additions in C++ 17. I don't know if there's still seats open for that. So the PETSc website used to be at Argonne National Lab, which is where PETSc originates, but these days it's at petsc.org. Probably if you use your favorite search engine, it will these days immediately find the petsc.org and not the MCS-ANL-Gov. Okay, introduction to the PETSc library. With apologies for the moving of the date, the frost and all that, threw a spanner in the works. Okay. So given how people describe themselves, I imagine that most of you do partial differential equations, sparse matrices. That's the sort of context that PETSc comes from. So Barry Smith, the project lead of PETSc, said at some point that developing parallel non-trivial PDE solvers that deliver high performance is still difficult and requires months or even years of concentrated effort. PETSc is a toolkit that can ease these difficulties and reduce the development time, but it is not a black box PDE solver nor a silver bullet. So it is a toolkit that can make it easier for you to put together a very sophisticated PDE solver or anything else that you want to do in parallel with linear algebra. Minjiang, repository link to what? In the Slack channel has them at the top of the screen. Patrick, thank you very much. Yes. So that's the repository that you need to clone on Frontera. So PETSc stands for Portable Extensible Toolkit for Scientific Computations, and so that means in particular parallel linear algebra. I think that if you want to call yourself an MPI parallel programmer, then once in your lifetime you have to code a parallel sparse matrix vector product just to appreciate the hassle that PETSc takes off your hand. So the sparse matrix is not that hard to code. Doing it in parallel is a considerable hassle, and so that's where PETSc gives you low-level tools that take a lot of work off your hands. PETSc is a toolkit. It contains both high-level and low-level tools. Let's see. So I am on the PETSc website. Let's go to the documentation link. It has a manual in PDF form. Actually, my textbook, so the one that you download here, Eijkhout Parallel Programming PDF, has a section on PETSc. It doesn't cover everything yet, but I'm working on it. So there is a manual, and then there is the manual pages, function index, examples index. I wonder what happens if you go to, no, that's not the one that I wanted. I want to show you how impressive PETSc is. And so this is the function index, which is very long. I haven't counted it, but I seem to recall that it was a few thousand routines last time I actually bothered to count it. Right, so this is an enormous number of routines, and many of them are very obscure, but there are high-level routines. So what I'm going to show you today is a number of the basic blocks. So I'll introduce you to the basic concepts and show you how to put together a linear system solver at least. Okay, Scientific Computations Toolkit. PETSc is portable. Basically any platform that has MPI, you can compile it on, even Windows. Well, given that you guys are all TAC users, you probably use mostly the Linux that we have on Frontera, but PETSc is installable on a Windows laptop if you would want to do so. What's in PETSc? So linear algebra tools, then linear system solvers, and there are nonlinear system solvers. There used to be a separate optimization library which has been rolled into PETSc. There are various support tools, so it's a mix of high and low level. So you have your application code, and then you can use PETSc time-stepping methods, nonlinear equation solvers, and those are all based on linear system solvers, and that is all based on the basic matrices, vectors, tools, and below all of that lives MPI and the basic linear algebra subprograms, which are pre-installed on the on machines like Frontera. So PETSc builds on MPI. Here is again a very short inventory of the sort of things that are in PETSc. Some of these names may mean nothing to you, but the documentation, go to petsc.org. Documentation is downloadable as PDF or usable as HTML. If you have questions about this specific tutorial, then mail me. If you run PETSc on your local cluster, ask your local support. And of course, if you run on Frontera or another TAC machine, then submit a ticket and it'll find its way to me. I actually prefer tickets over you mailing me. General questions about PETSc, so not specifically about this tutorial or about running on Frontera. There is an extremely responsive PETSc mailing list. They have perfected the debugging over email to a high art. Oh yeah, is everyone logged into Frontera? So I assume you're sort of familiar with the TAC workflow. I hope my windows are all readable. So if you're familiar with TAC machines, we drive our software with the module system and module list. Huh. Someone must be banging on the file system. We'll see that in a second. So there is a PETSc module, and so you can look at the example codes that are in the PETSc directory. So with all the stuff that PETSc contains, PETSc doesn't do everything, but fortunately it can interface to a whole bunch of libraries. So scalable is one of the very few distributed dense linear algebra libraries, and PETSc can interface to that. So wow, Frontera is hanging. If you so there is grid partitioning software. That is again something that the PETSc developers are not experts on, but PETSc can interface to it. ODE solvers, optimization. There is a eigenvalue library called SLAPC, Simple Linear Eigen Problems Computations, I guess, that comes out of a university in Spain. And these days, when you install PETSc, you can immediately integrate it. Okay, so Frontera just reported that it has loaded the Intel library and Intel MPI. Python 3, so I hope all of the people that speak Python have moved on from Python 2 to 3. So module avail PETSc, and yeah, there's too many modules available. I wonder what's keeping Frontera. So PETSc is layered on top of MPI, and MPI does the basic stuff, send a buffer of reals between two processors. PETSc has the intermediate level tools like construct a matrix by inserting an element in it. PETSc is very transparent. The same code can run sequentially and parallel, with some footnotes to that. But basically, you don't have to know much MPI when you use PETSc. All the simple things that you want to do in MPI have gone into the PETSc tools. Because PETSc is based on MPI, and I assume everyone here speaks a little MPI, I hope you know what a communicator is. And so all objects in PETSc are based on a communicator. PETSc is basically completely MPI parallel. There is no OpenMP or threading in the library. On the other hand, there is GPU support. I have played with that on the Frontera RTX nodes, and it does not give a lot of performance improvement. GPUs are just not the thing to do when you do sparse computations. I have not tested this yet on the Longhorn system, which is IBM Power 4 and NVIDIA, V100 or something. So maybe they perform better. That's on my to-do list. Okay, so what PETSc modules are available? Yeah, first of all, just for backward compatibility, I never remove an old PETSc installation. And PETSc comes out with a new version every half year, I think. So over the course of the life of Frontera, we've now accumulated 3.11, 3.12, 13, 14, 15, and currently 16. And if you look at the 3.16 PETScs, then you see that they come in complex debug. So one of the idiosyncrasies of design of PETSc is you cannot have a code that works in real and complex at the same time. It sort of makes sense, right? Your application is either real or complex numbers. And so you need to have separate PETSc installations for that. So, but if there is complex, there is a debug complex. I64 means that all your integers are 8 bytes. So if you have really large indices, then use one of the I64 installations. On the other hand, okay, some user the other day wanted single precision complex, so this is part of the installation these days. But normally you would use PETSc 3.16 and PETSc 3.16 debug. RTX is the one that uses the GPUs. And if you want a non-MPI PETSc, there is the Uni. But like I said, 3.16 and 3.16 debug. Okay, so today do module load PETSc 3.16 debug. So the thinking is that you load a debug version while you're developing your code, and then if you have confidence that it works nicely, then you load the production non-debug version and you run your code with that. Is there, does anyone run a mostly complex numbers code? Post in Slack if so. Let's see, what did you... Can we use RTX with Fortran? Good question. I would prefer questions in Slack because this require the Zoom chat requires me about 4 clicks or something to. But RTX with Fortran. Yes, that is absolutely no problem because the Fortran is only the user interface to PETSc and the whole library is written in C. So yes, that is absolutely no problem. Good question. Okay, PETSc has an object-oriented design. Once you have a matrix and a vector, and your matrix can be dense, sparse, whatever. Once you have a matrix and a vector, you say mat mult, and it multiplies them together. So it's sort of object-oriented polymorphism. It's kind of interesting to see under the covers how they actually did that. Right, and to support this sort of polymorphic design, they've had to hide stuff in function calls, so you cannot just say Aij becomes whatever. You have to do a function call for setting a matrix element. That sounds a little wasteful, but really the function call overhead is basically negligible compared to what you actually do in computations. Okay, so just a small word about the PETSc programming model. If you write PETSc, it's almost like you're writing sequential code. That is because PETSc is based on MPI and it uses the single program multiple data model. So you write a code, and with MPI, your code is executed on all of your nodes, processors, cores. So this comes from the MPI mindset, where in 1993 or so, when MPI first came out, a gray box from Compaq had one processor chip, and that could run one scientific code at full efficiency. So these days we have a complicated setup with multiple chips per node, and each processor chip has multiple cores. But still, we sort of pretend that we are in an MPI, in a pure MPI world. Hybrid programming with processes and threads we don't do in PETSc. Of course, it is possible that you use OpenMP or threading in the non-PETSc part of your code. There is absolutely no problem with that. Right, that is basically what I said. Yeah, so sometimes by mistake I will use the word processor, but that word is ambiguous. Is that a processor chip, or really a core is like a processor? So I'll try to use the word process as much as possible. Okay, so the single program multiple data model means that everything is symmetric. So you have to think that your executable runs in identical copies on all your locuses of execution. So there is no master or main process. There's a whole bunch of processes that all start at the same time. If you've done MPI, post in Slack if MPI is unknown to you. If you know MPI, then this is all familiar to you. So PETSc programs, being MPI based, are compiled with MPI compilers, and I assume you have done parallel runs on Frontera before. So let's, how many people do we have today? Lauren, did we set up 1 or 2 nodes per participant?
We set up 2 per participant. There should be 60 nodes.
Okay. Let's see, let's do iDev, and I think we're going Lauren, how is today divided? Twice 3 hours or 3 times 2? What are we doing?
We have the reservation from 9 to 4.
9 to 4. Okay. Let's see. So 9 to noon and 1 to 4 with a break in the middle. Unfortunately, we cannot make an iDev session for 3 hours because we're in the development queue probably. So let's do iDev minus T 1 hour 30 minutes and 2 nodes and a total of 10 processes, just not to clutter the screen. So I'm starting an iDev session. This is known to everyone, I hope. And I set it for 1.5 hours. Normally it times out after 30 minutes, which usually means that you're in the middle of an editing session. So let's do 1 hour 30. And this will come back at some point. I'm not sure what's slowing down Frontera today. Okay, so PETSc programs are compiled with the normal MPI programs, and you use IB run. I don't see anyone protesting in Slack, so I assume this is known to everyone. Questions in Slack, please. Don't hesitate to ask. Given how few people we have online, you can even unmute yourself if you wanted. 13 participants. You can even unmute yourself and ask questions that way. I don't mind. Okay, iDev says there is an active reservation. Yes, use that. And so I assume you know that you can develop parallel programs on your laptop. Unix will use time slicing, or Linux. It's not going to be terribly efficient, but for just program development, it's good enough. This sort of cluster stuff, you know. Right, so the problem of parallel output, if you have a program that says hello world, then you get a whole bunch of crap on your screen. So the first thing we'll do, just as a warm-up, is do hello world with PETSc. Okay, PETSc programs. Lordy, why is this so slow? C++ programmers, you will be using the C interface. So you have to do include petsc.h. No one has volunteered that they are a Fortran programmer, but I'll just mention it anyway. In Fortran, you need both an include file, which has the C preprocessor, the CPP, type defs and all that, and after that you use you load a PETSc module that has all the function signatures. The PETSc installations at TAC all include a Python interface, so from PETSc for Pi, import PETSc. The PETSc for Pi used to be, it is a project that comes from a separate researcher, but it's pretty complete. He's the same guy that also wrote MPI for Pi. So it all acts very similarly. Is there anyone that thinks they are going to be using PETSc from Python? Feel free to leave comments in Slack. And so through the miracle of type defs and the C preprocessor, in C and C++, it looks like PETSc. You have used PETSc from Python. Cool. Yeah, I once used PETSc for the linear algebra to analyze an email database. So I parsed the emails through Python and then put the data straight into PETSc linear algebra. Sometimes it makes sense to do that sort of thing. Oh, and there are packages like Firedrake and Phoenix that are Python based but use PETSc underneath. So, right, it perfectly makes sense to do PETSc from Python. In C, you have variable declarations. So a KSP is, for historic reasons, the type for a linear system solver, matvec. PETSc has its own integers and reals, and so you don't have to worry about short, int, long. It's determined by the installation. Note that there is both a PETSc scalar and a PETSc real. If you have a code that is in complex numbers, then PETSc scalar all of a sudden becomes a complex number. If you run the same code with an installation in real numbers, then PETSc scalar is a real. However, if you are running in complex numbers, the norm of a vector is still a real number. So distinguish between a PETSc scalar, which could be a real or a complex. So you will mostly use PETSc scalar in your code. That is what's in your matrix and vector. But once you compute a norm of something, it's a PETSc real. In Fortran, it looks the same. Yeah, Python doesn't have a type system, so no slide about Python. You have to initialize the library. So there is a PETSc initialize call. It looks a little like MPI in it. So it takes the argc and the argv, and you can give it a couple more arguments that we will get around to. If MPI is not initialized, then PETSc initialize will initialize it. So if you write a PETSc code, just put PETSc initialize and PETSc finalize all the way at the top and the bottom of your main program, and that takes care of MPI too. Now, in MPI, every routine has an error parameter, and I always tell students just ignore it because there's no way you can recover from a parallel error. In PETSc, likewise, every routine has an error parameter, and it's a good idea to catch it and then invoke this macro, check error condition with your error code. If you do that, then PETSc will give you a very nice trace back in the case of errors that it can find. Even with segmentation faults, it can sometimes give you some useful information. So make sure to catch each error and use that macro. just a couple of extra keystrokes, and it's very useful for debugging. Fortran does not have argc, argv, so it's PETSc initialize. C is very tolerant in how it handles 0 and null. The Fortran interface does strict type checking, and so for every null, there is a PETSc null character, there is a PETSc null whatever, boolean, logical, whatever. So anyway, in Fortran, PETSc initialize, finalize. In Python, the initialize is done by the import call, so that's easy. A word about data type. PETSc basically has its own reals, ints, bools, so use those rather than the native ones from your programming language. Because, for instance, if you write your whole code in PETSc ints, then you can easily switch to 64-bit int if necessary. Okay, so yeah, on the tag module system, there are a couple of routines that have I64 in them. So those are the ones that use 64-bit integers. I already mentioned the existence of debug routines. Let me silence that thing. Okay, let's get our feet wet and do an exercise. So in the exercises directory, I go into exercises MPIC. Everyone that chimed in on Slack is doing C or C++, so C it is today. Here's a... let's clean that up a little. Oh, sorry, wrong one. See the exercises PETSc C. And clean up here. There is some... I need to... my make clean rule is not perfect. Okay, so there is a hello.c, and if you take a look at that, you're doing Fortran. Ben, where do you get the exercises? Are you showing the whole? At the top of the Slack channel, there is a repository with exercises. So go to that link and do a git clone on that one. So there is a PETSc printf, which unfortunately is a little hard to use, a little harder in Fortran than in C. So why is the solution here? It's not supposed to be. There. Is Frontera equally slow for everyone here? Okay. I'm sure that some operator is tracking down the user that is doing too much file. Okay, I hope this is what everyone has. I'm not sure. I guess my repository is polluted by teaching before. So let me just make a clean clone. I go to Scratch. Browser, no, that one. Copy that one. Git clone. Oh, git clone. Yes, the file system is shared between users. So if a user writes a code that you have your old PC code that does a checkpoint per second, and now you make it parallel and you run it on Frontera on 1,000 processors. All of a sudden you're opening 1,000 files per second, and the file system doesn't like that. So yeah, the file system is really the bottleneck in a cluster like this, and we regularly have to track down users that have badly written file I/O. Okay. Parallel programming public exercises PETSc, Emacs, hello.c, and okay, here we have the exercise. So normally you would do printf, and I have my, let's see if my make files work today. Make hello, and then IB run hello. Okay, so what I want you to do is use PETSc printf. So PETSc printf looks like Fortran printf, so it looks like C printf with a format string and then the arguments, except that it has a communicator. So in C, it's easy to use. In Fortran, unfortunately, variable numbers of arguments don't work. So in Fortran, you have to construct your own character string. In Python, it's PETSc sysprint, which is a class method, and then you print whatever you want to print. Oh, the keyword arguments need to include the communicator. Okay, this is no fun. I don't see anything. Okay, so the problem with normal printf is that every you're running SPMD parallel, so each process is printing the printf. So and often you only want one incarnation. So PETSc has a utility routine that basically does if I am process 0, then printf. So this is a case where, as quite often, PETSc has very convenient utilities for doing, for assisting in the programming. It's not just a parallel linear algebra library. Thank you, Lauren. Oh, keyboard was hanging from my other computer. Yeah, so in Fortran, unfortunately, you need to do a. I hope this idiom is known to the Fortran programmers. So you write into a string and then you print the string. Okay, so I will, if I show a PETSc routine, then often I will display it like this as a function signature or prototype. So I hope everyone can read this. If I say PETSc error code vec create MPI com whatever, then that means that this routine returns a PETSc error code, and so you need to declare a variable PETSc error code, and that routine returns that. And the first argument is an MPI communicator, so you need to have a communicator and you supply that. I hope everyone is conversant with this notion of function signatures and the use of the function. In Fortran, the distinction is not that clear. Oh yes, if I, in many cases, I will only show the C version of a routine, but the Fortran always has the final error parameter. So I'm not sure why PETSc is not yet making that optional. In Python, there are object methods and class methods, and I will try to indicate which one is which. So, so for instance, in Python, a matrix is a PETSc mat, and then if you have a mat object, then you can set its size. And so how do you do that? Well, you create a PETSc matrix and then you set its size. On the other hand, some routines are class methods. Again, Python programmers, just be aware of, I may give the signature of the function, and of course you need to translate that into how you actually use that. Okay, so I had a code that had a bare printf, and now you need to figure out how to turn that into a PETSc printf, because you know this phenomenon that a printf statement will come from every running process. Okay, why don't I give you a couple minutes and you can do that exercise. So the exercise is look at PETSc printf and then have your program spit out. This program runs on 27 processors. Okay, timer for a couple minutes, and that gives me an opportunity to get a glass of water. Oh yes, and compiling and running is make and then IB run. And that was the timer. I assume that no one had a problem with that exercise. Any problems compiling, running? Good. Yeah, so PETSc has a whole bunch of utility routines that make program development a lot more pleasant. PETSc has its own alloc, malloc, and free, and that one has the facility to do memory corruption checking. It's pretty cool. Okay, PETSc printf prototypes. Yes, this is kind of cool. So PETSc initialize can take a couple of arguments, and the fourth argument is a string, and so you can put a help string in your program, and then if you run your program with help, it will spit that out, as well as a whole bunch of other things. PETSc, if you put PETSc function begin user and PETSc function return at the top and the end of a subroutine, then PETSc can incorporate that sort of information in tracebacks. So, okay. Let's see. I mentioned that every PETSc routine returns an error code, right? Okay, so now if I write my own routine, so I return an error code, and so I have a function that does nothing but just throw an exception in, to put it in C++ terms. So set error q is not sure where the q comes from. Anyway, set an error, and so this function errors, and now if you run this, see it spits out, it sets a message, we cannot go on like this, and so now PETSc reports that main on line 30 called a function, this function bombs, and line 20 generated an error like this. Anyway, so the traceback knows the name of the function, and so you don't have to go into a debugger and find the stack trace. So this is really convenient. So PETSc has a bunch of these tools for error handling, and so that's the reason that you want to go through the slight overhead of putting PETSc function begin, function return around every routine that you write. Yeah, okay, so if you want to test yourself on this, you can write a function square root that either returns it or it errors if you give it a negative number. Let's stay with utilities for a minute. this is ultra cool. PETSc is very good at parsing command line arguments. So if you know the phenomenon that you have a code and you want to change parameters, you want to change settings, and you wind up either editing the source and recompiling it with a different value of whatever, or you have to edit an input file. So PETSc makes that sort of thing very easy by having command line arguments. There's a whole bunch of routines, PETSc options get something. So you can have flags, but in this case, PETSc options get int means that if there is a command line flag -n, then the value is put in the integer n, and it reports back this flag saying that yes, this option existed. This also works in Fortran. Note that in C you can simply say PETSc null. In Fortran you have to tell it what kind of a null it is, because the Fortran interface does strict type checking. This sort of stuff also works in Python, where PETSc options get int. Let's see. Am I using this somewhere? Yes, so this mechanism is used in a couple of the examples that you will do today. Yeah, let's not go further into this. Okay, so that's a bunch of utility stuff and general notions to get out of the way. But this is really cool, the command line options. So makes it very easy to change settings from the command line and have defaults in the program. PETSc does all the scanning and conversion here for you. And you will see more about command line arguments a little later. Okay, yeah, I checked with the sysadmin what was happening with the system, and user has been found and has been banned. So yeah, if you don't want to lose your account for a while, don't do too much file I/O. If you have questions about file I/O, submit a ticket in the ticket system, and some of my very knowledgeable colleagues have developed tools for optimizing file I/O, and there are some guidelines in the user guide, and we have a couple of tools developed by colleagues of mine to help you. Yeah, since there are people doing Python, imagine what happens if you start Python on 4,000 cores. Each core loads the whole Python executable and all the libraries. This is no fun. This just starting the program is stress on the file system. So one of my colleagues has developed a tool especially for just starting Python. Anyway, let's go into the data types. So everything in PETSc is an object. Yeah, PETSc is written in C, but it uses sort of a object-oriented style of programming. If you want to know how to do polymorphism in C, it's kind of cute to look at the source of PETSc. Anyway, so everything in PETSc is an object, and it has a create and a destroy call, and that holds for both things like vectors and matrices that are object-like, but it also holds for things like a solver or a viewer, which are not really objects in a sort of tangible sense. Anyway, you create it on a communicator, and then you destroy it when you're done with the object. So in the exercises today, the destroy calls are of course not terribly necessary, but if you write a serious program, prevent memory leaks by doing destroy on all your objects. Okay, so in C, you declare your vector object, care of the C preprocessor, and then you create and you destroy it. Note that the destroy call also wants the address so that it can zero out the pointer. In Fortran, remember the error code at the end. Oops. More about vectors. So a vector is, PETSc in some sense tries to think in application terms, and so a vector is not just an array, but it's something you can do linear algebra on. And an array of integers is not in a vector space, and so there are no vectors of integers. A vector consists of scalars. The only arrays of integers that play a role in scientific computation are really indices into whatever, and there is a data type for that. Okay, vectors. So there is the create call, but that really only makes kind of the bookkeeping. It doesn't actually allocate anything. For that, you first have to tell PETSc what type of a vector it is. Is it an MPI vector, meaning distributed, or is it sequential? And so if it's sequential, then each process has elements 0 through 100 or whatever. If it's an MPI vector, then the first process has 0 to 100, the second one has 100 to 200, etc., etc. So if you make it an MPI vector, then it's really a distributed object. Okay, after you set the type of a vector, and there's essentially only two types of vectors, but for matrices it gets very complicated. There are many types of those. So when you set the type of a vector, you have to set the size, and so PETSc usually thinks in distributed memory terms, and so there is the local size, which is the lowercase m, and there is the global size, which is the uppercase m. Once you have created a vector, you can duplicate it and say make another one like that, so you don't have to remember how you created the first vector. Yeah, the create calls in Python are a little weird, so just remember this idiom. So PETSc vec dot create, just saying PETSc vec does not, I'm not sure what that gives you, but you have to do a create call on it, and then you have the vector object, and you set its type and its size. Yeah. By the way, for C++ programmers, let me mention, in case you ever need to write MPI code yourself. I don't know if it irritates you that the C interface is so terribly clunky in C++. I have been playing with a library called MPL, message passing layer, I guess, which is a C++ interface to MPI. I thought I'd mention it. It's very elegant, and it actually looks like idiomatic C++ 17. Okay, so you specify the sizes of a vector, the local size and the global size. But there is some redundancy in that, because if every process specifies the local size, then the global size can be deduced from that. Likewise, if you have no reason to do load balancing in a non-trivial manner, then if you have a vector of size 1,000,000 and you have 100 processes, then it's clear how you want to divide it. That's 10,000 per process. So there is a parameter called PETSc decide, and so you can say my global vector is size 8. I have 3 processes, and so I'm leaving it up to PETSc to divide it as 332. On the other hand, if you have an application where the local size of the vector comes from some adaptive refinement process, then you may know the local size, but you don't know the global size. And so it's also possible for every process to specify the local size and leave the global size as PETSc decide. Of course, you can also specify both of them. In Python, the size is a tuple of local and global, and again, PETSc.decide exists. Now, if you distribute your vector in a non-trivial manner, do you have to remember that sort of stuff? No, PETSc has a lot of query routines. So once the vector has been constructed, you can do get size, which gives you the global size, get local size, which gives you the size on that process. And you can also do get ownership range. So the ownership range, so vectors are distributed in a naive manner. Every process has a block. That may sound like a bit of a limitation, but it's not really. Anyway, so every process has a block of indices, and so you can get the ownership range, meaning the low, as in the first index that you have, and the high, which is the last. No, it's the one more than the last, which is because in C you write a loop as starting on the upper bound and starting at the lower bound and non-inclusive upper bound. So that's the sort of idiomatic way of doing it in C, and that's why PETSc does low and high is one more. So if you have 8 elements divided over 3, then on the second processor, which is process 1, the low is 3 and the high is 6, because that's one more than the lowest, than the last stored variable. You can even do a PETSc split ownership. So if you know the global size, it will tell you what is the local size on that object or on that distribution. Okay, for testing, it's often convenient to set a vector uniformly to one value, so vec set. But most of the time, if you want to set a vector value, you use the routine vec set value. So you have a vector, you tell it what index and then what value, and then there is the insert mode. So the insert mode is either insert values or add values. And the index is not the index on the process, but it's the global index. So it is in fact possible in PETSc that process 0 sets every element for every other process. So PETSc is extremely flexible in how it handles parallelism. It's almost like you're writing a sequential code, right? Because you can set any element. Of course, at some point, if process 0 is setting all the elements, at some point it has to communicate that to everyone else. And so this is one of the cases where design decisions under the hood are slightly visible to the user level. So after you set all your vector elements, you do assembly begin and assembly end. What happens here in MPI terms? Post in Slack. Why is there a begin and an end? Okay, so vec set value in C, it's vector I, yeah, C and Fortran, it looks the same. Whoops, the Fortran is missing the error code. There is also vec set values. So if you're doing finite elements and you evaluate element integrals, then it may make sense that you have a set of indices and a set of values nicely contained in an array, and so there is the plural vec set values, plural, which takes an array of indices and an array of values. And of course, you have to say how many. Well, people post in Slack, why is there a vec set? Why is there an assembly begin and an assembly end? In Python, this does the, so here is the illustration in C and Fortran. It looks pretty much the same, and in Python you can specify a Python list. No one? Okay, the assembly begin does posts the I sends and the I receives, and the assembly end does the MPI wait. Okay, so once you create a vector, what's the optimal size of the array in vec set values? I don't think there is an optimal. So you don't have to worry that setting multiple values is less function call overhead. Constructing the matrix is really, if you do a Newton iteration with a complicated Jacobian, and each step you solve a linear system, then creating the matrix is basically negligible. So don't worry about function overhead. So if your application naturally gives you, for instance, because you do element integrals, if your application naturally gives you an array of indices and values, then use the plural set values. Otherwise, just do a whole bunch of set value calls. I wouldn't worry about that, about overhead. I hope that answered the question. Okay, so vex set create a race condition. Yes. Well, more like undefined behavior. Yes, I see what you mean. Different processes specify the same element. It's undefined behavior, so don't do it. But note that there is add values. So again, if you're doing finite elements and you get contributions from two elements to the same value, then you would set the vector initially to 0 and then you add the contributions. Okay, so that is safe. If you do multiple inserts on the same element, it's just undefined behavior. See, underneath PETSc, it does MPI messages and then it inserts it. And so it depends on the order in which messages come in. And so it's not a race condition. Well, yeah. All right. Yeah, it is a race condition. Just don't do this. Okay, so your vector data structure hides from you how the data is stored, and so basically you need a routine for every operation. So for vector additions, there's XP. Scaling a vector by a scalar, there's vex scale, there are dot products, norm, sum, swap two vectors, pointwise operations, max, apps, reciprocal. Yeah, so there's a whole bunch of operations, and if one is missing, then pay attention. Okay. I've been talking for long enough. Let's take a 10-minute break. And then, right, so we'll go in 1.5-hour segments. And so in 10 minutes, we'll be at the end of the first 1.5-hour block. Okay? Okay, I'm back. Sound, video. Yep. Okay, let's do a simple exercise. Did anyone already work on this on the break? So let's see. So there is a vec.c. Let's see what happens if you compile it. Yeah, there's code missing, so it's an exercise. Create a vector where the values are a single sine wave. Okay, so what do we have? PETSc options get int. So this program takes a command line option for the size of the vector. By the way, note that this is very common in this is very common in PETSc routines. So, for instance, the getInt returns the value and it returns a flag saying that there was a value. Now, if you're not interested in that flag, you can actually put a null there. So in many PETSc routines, if there is an output parameter and you're not interested in it, you can specify a null. I love that idiom. It's very convenient. You don't have to declare a variable that you're then not going to be using. Okay, so the command line argument n is the global size of the vector because it says vec create and then set sizes PETSc decide for the local and n for the global. Set from options, yeah, you can. We'll get to that. You can specify more command line options, and then if there is a set from options, then they get parsed at that point. Make another vector y that it has the same. Set x to 1. So the first exercise is set y to a sine wave. So what are we doing here? So we want to know the global size of the vector. We have the local size and we have the ownership range. Okay, so this is kind of redundant. I don't need all of these. So what I want you to do is, so this loop loops over the local part of the vector. Loop over the locally stored part of the vector. And then so the value is 2 pi I over n, right? 2 pi I h. And the h is 1 over the global size, maybe plus or minus 1. I have to think about that. No, I think this is correct. Or maybe not. Sorry. Anyway, 2 pi I h. And then you have to fill in where that element goes. So the only thing missing is what index it goes. And then you assemble the vector. Let's see, let's disable the second part. So okay, do you want to do this on your own, or yeah, I'll give you 3 minutes to think about this. So what indexes are you using, and where are you going to put this in the vector? Okay, and then disable the rest of the exercise. So if 0 and if. Okay, 3 minutes. And as it says in the exercise slide, then when you run it, add the option vec view. Okay, did everyone figure it out? Did anyone get any interesting error messages or erroneous behavior? Post in Slack if you saw something interesting. So did anyone write index is 0, index less than local size? Did anyone write this? Ben, that is interesting. I'm not sure how you would do that. Maybe would you be willing to share your screen? So let's see, make vec ib run vec. I have 10 processes, so let's do 15 and vec view. And here we go, and yes, it's a complete mess. It's wrong, it's wrong. So when you write PETSc, did anyone do it this way? How about my first plus index? So you number through your local indices, but then you know that you have to put them somewhere further. Let's see what this does. Yeah. Maybe this is what you did, Ben. Anyway, so if you write PETSc, you really have to think in global terms. So this process has indices from my first index less than my last. Right. So you write a loop in global indices, and you set the value in the global index, and then PETSc, of course, translates it under the hood as, okay, this global index is locals, and so I can just insert it here. Oh, what did I miss? And this looks plausible. Process 0 starts at 0, and then it goes up, and then it goes through 0 and negative. Yep, that looks like a sine wave to me. Ben, still problems? If you want to share your screen, I can let you do that. That was the issue. Yes. Okay, very good. What was the second part of the... Oh, by the way, so I ran with the option vec view, and where in the code did it say to view this thing? It didn't say, but whenever at the assembly call, that's where the view command line option gets inserted. See, if I don't do this, it just runs and gives 0 output. So this is really great. If you have doubts about how your program works, just put a view call on the command line, and you get output without specifying, without recompiling and all that. Okay. Yeah. Okay. So more cases of overlapping computation communication. Dot products have a begin and an end. So I said that most of the times you will set your elements with calls to how does PETSc know which vector we want to view? Whichever one you're assembling. And there is actually a way to give a vector a name and then add that name to the vec call, but I think it will print out whatever you're assembling. So whenever you do an assemble call, it will show it. Which MPI non-blocking functions? Oh, yeah, good point. that is actually a good question. So I think PETSc does its own collective. It probably does. It does not rely on the built-in collectives because then it cannot overlap. But this mechanism existed before MPI got the non-blocking collectives. Good question, Nick. I'll have to get back to you on that one. Yeah, so PETSc implements its own collective, and so it can do something that MPI cannot. For instance, a dot product and a norm are almost the same reduction, but well, okay, a dot product is a plus reduction, and a 2 norm is a plus reduction. But let's say you do the inf norm. The inf norm is a max reduction. In MPI, you would have to start separately a plus and a max reduction, whereas in PETSc you start the plus, you start the max, then you end the plus and you end the max, and it will do a double reduction on multiple operators. So PETSc is still a little more flexible than MPI. Just notice that. Okay, right. So most of the time you will use vex set value or values for setting the elements, but it is possible to immediately access the underlying data structure. So, for instance, if you have an array that is in, oh, I don't know, memory mapped stuff, or for whatever reason you want to create a vector from your own array, then you can do vec create sec or MPI with array. And also, if PETSc has created the vector for you, then you can do get array and restore array. So with get array, you get a pointer to the underlying malloced data. And just for cleanliness, PETSc insists that you then restore it. In fact, there is even get array read if you need it only for read-only purposes. Okay, so how does that go? You declare a pointer to PETSc scalar. You have your array. You do vec get array, and after that you can iterate over the local elements, and you restore it to tell PETSc that the array will no longer be touched and there are no conflicts. There's a couple more routines: place array, replace array, and so yeah. Sometimes you have a vector data structure, but you want to replace the data with something else. I used that the other day, but I don't remember why. So in C, you make a pointer like that. For Fortran 90, there are nice routines. They have a slightly different name. In most of the cases, the C and the Fortran routine have the same name. But in this case, the Fortran routines have F90. In the name, and so you get a pointer returned. The original Fortran version of get array does something really ugly that works with F77. Okay, so we've done vectors. Let's do matrices. Right, a matrix is again an object, and so there is a create and a destroy call. You have to set the type, as with the vectors, and now there is a bunch of matrix types. Oh yes, when the Frontera was hanging, I wanted to show you so I'm now in the PETSc directory, so that's home1 apps, which is the system location for applications under Intel MPI PETSc 316. And if you do an ls, you see subdirectories for all the installation types. So let's go into CLX, which is Cascade Lake. Oops, that's not what I wanted. I wanted to go into the source directory. And then there are subdirectories for all the types. So let's go into KSP. For some reason it has a subdirectory KSP. Oh no, let's go into mat. That's what I think impulse probably. Matrix implementations. Where is the dense? That's of course in dense. Sequential. And then there is dense.h. Yeah. So the source of PETSc is set up quite logically. Actually, this is not what I wanted to do. I wanted to go to, where are we? I wanted to go to the include directory and less PETSc mat.h. And here you see all the matrix types. This is what I wanted to do. So I'm in PETSc dir /include, and then there is an include file for every matrix, for every PETSc object type. And so you see that there is Aij, which is sparse. There is a single processor sparse, multiprocessor sparse. Let's see, where are the dense types? There is a dense matrix, which is interpreted depending on the circumstances as dense CUDA, dense sequential, dense distributed, dense distributed CUDA. So there's a whole bunch of matrix types. So if you're ever curious, I think the documentation does not necessarily list all of them. But you can always look it up in the source pretty easily. So where was I? I was in PETSc dir include. PETSc dir is one of the environment variables, and the other one is PETSc arc. So those two determine which version of PETSc you're using. Okay, let's go back. That was to illustrate that there is a whole bunch of matrix types. For a matrix, you have to set sizes as local row size, local column size, global row size, global column size. Now, some of this is a little confusing. Considering that PETSc is mostly about linear systems and eigenvalues, it mostly deals with square matrices, but every once in a while you have a non-square matrix, and then it's kind of hard to think about the local and the global row and column size. But for square matrices, it's easy enough. So again, use PETSc decide if you know the global size, or if for whatever reason the local size is determined by something. And this routine we will get to in a second. This is important. If you already have an existing matrix, then there are a couple of routines. Okay, do not do this unless you interface to a legacy code. So you may think that it's convenient to construct your matrix with your own code and then tell PETSc, okay, now turn it into whatever you want. It's much better to completely make PETSc pervasive in your code and do everything with PETSc, including creating the matrix. So there is really no reason for using your own naive code to create the matrix and then pour it into PETSc. You should really use PETSc throughout. Okay, pre-allocation. So if you have a dense matrix, it's pretty easy to allocate that, because you have the row and the column size, and so you malloc m times n times size of whatever your real type is, scalar type. For a sparse matrix, that's much harder. You can have a sparse matrix that only contains a diagonal, or that contains 3/4 of the elements being non-zero. And PETSc is extremely flexible. So because there is no preset sparsity pattern and any processor can insert something in any element, how would you do that under the hood? Well, so you could think PETSc allocates completely dense matrix, and then when you start using it, shrinks it in, but that's an incredible waste of space. Or you could think PETSc creates only, say, the diagonal, and then gradually adds elements, but adding elements is not possible, right? Yeah, in C++ you have pushback and capacity, but all of that works by reallocating the underlying data structure. And so if you do this naively in PETSc, then for a simple application, 3/4 of the running time of your program goes into constructing the matrix. Okay, so again, the PETSc implementation comes to the surface a little, and you have to tell PETSc what the sparsity structure is. Somewhat. Okay, so if you have a 5-point stencil, then it's easy. You tell PETSc every row has 5 non-zeros. That wastes a couple of locations, but you don't care, right? So for simple stencils, that's easy. And I see that my IDEF session just ended. So for simple stencils, it's easy to specify the sparsity structure. For more complicated structures, you may find yourself writing the matrix construction loop twice. So first you go through your matrix construction and you only count how many non-zeros per row. Then you allocate the matrix, and then you do the construction again, doing the actual element integrals or whatever. At some point, the PETSc developers got fed up with people asking why is constructing the matrix so expensive, and so now by default the option that you're allowed to create new non-zero locations is false. And so if you specify a non-zero outside of the initial sparsity structure, then your code will abort with an error. Okay, so that initial sparsity structure. So let's look at the simple case. A sequential Aij, so that means a single processor sparse matrix. In that case, you can do two things. You can either say every row has this many non-zeros. So for a Laplacian 5, and that wastes a couple of elements, but you really don't care about that. Okay, so you can say 5 there, and then for the second argument you use null or PETSc null. If your matrix is very irregular, and so let's say it has a million rows, and there is one row that has 10 times the number of non-zeros of every other one, then saying every row has at most this many non-zeros is gross overkill. And so you can actually give PETSc an array of integers that says this row has this many, that row has that many, that row has that many. Okay, so that's why you have the notion that you do the matrix construction twice. Once to count how long every row is, and once for actually filling it in. Okay, so like I said, there's two ways of doing it, and for the option that you're not choosing, just put null there. In Fortran, you have to be a little more careful and say PETSc null integer. Okay. Now, this was a sequential, meaning single processor matrix. This sort of thing becomes a little harder in parallel. So here you have to understand a little about how PETSc stores its matrix internally. So PETSc uses compressed row storage format. Everyone knows what compressed row storage is, I hope. It doesn't matter if you don't. So PETSc uses compressed row storage, and so it could use, okay, I said that vectors are partitioned by contiguous blocks. Matrices are also distributed by contiguous blocks. So a matrix is distributed one-dimensionally. Has anyone here taken my scientific computing class? No, I don't think I recognize any names here. Okay, so PETSc divides the matrix by block rows. What other options are there? Post something in Slack if you want. So each process stores a block row out of the matrix, but it doesn't store that as a single matrix. It cuts it into two pieces, namely for whatever rows you have, those columns, so it's a square diagonal block, that goes into one compressed row storage matrix, and then everything else goes into another compressed row storage matrix. Okay, PETSc divides by block rows. How could it have done it otherwise? Two options. So why does PETSc do this? Well, if you imagine how you multiply a matrix times a vector, so that's inner product of row and the vector, then your matrix is distributed, your vector is distributed, and the diagonal block multiplies with the elements of the vector that you already have that are stored locally, whereas the B part multiplies with vector elements that need to be communicated from another process. So y is a times x gets split up into the A part of the matrix times the local variables and the B part of the matrix times the non-local variables. And so what PETSc does here is yet another application of overlapping communication computation. So you start your MPI iSense receives for the non-local variables. You do the A multiplication part, you wait for the B stuff to come in, and then you multiply the B part. Okay, so this is one of the places where PETSc's internal design is slightly visible to the user. So it would have been possible to make this interface simpler to use, but that would have cost performance. So there's a minor trade-off that you put a slight burden on the user to make the code more efficient. Okay, but now you have the Aij pre-allocation, which is number of non-zeros or array of number of non-zeros. Now you need to do that here, and so because you have two parts, PETSc needs to know how much to allocate for both, and so how many non-zeros in the diagonal part, how many non-zeros in the off-diagonal part, or explicit counts. Okay, so now you have to think a little. If this is a 5-point Laplacian, is that 3 and 2? No, it's not. If your block size is bigger than the row length of your Laplacian matrix, then it's probably not 3 non-zeros and 2, but 4. But you can have 2 in the off-diagonal part, and so this wastes a little space. You have to think about it carefully. Yeah. So just like with the vector, you can do matrix get size, get local size, and that gives you the row and the column sizes locally and globally. Ownership range, because it splits it one-dimensionally, is the first row and the last row. And if you're only interested in the first row, then you can specify null for the last row. So query routines, you can usually specify null for the values that you're not interested in. Okay, mat set value. It's again, as in the vector case, you give it an index, you give it a value, and now you need to give an ij value index. Insert mode is insert or add. If you're doing element integrals and you can specify a block of values, then you can do it like that, saying how many row indices and the row indices, how many column, and then a block of values in C ordering, so ordered by row. setting one element, setting multiple elements. Yeah, if you want to set one element with the general routine, then you need to specify an array of indices, so it's one, and when you're done with the matrix element insertion, you call assembly begin and assembly end. All right, you cannot mix inserting and adding values, so you need to do a flush assembly in between the two. Is this a fun exercise? Oh, why not? See the exercises PETSc, Emacs, not VEC. Okay, so I have a routine. Create matrix, which does something tricky. Let's see if can I compile this. No, stuff missing, so let's disable that for a second. More stuff missing. Mat flush assembly, when to use that? That is for the case that you want to set certain matrix elements and other matrix elements you want to add to. So it's not allowed to insert certain elements and add to other elements. So you need to have separate stages. Say first a stage where you set certain elements and then a stage where you add to some of them. Eventually you have to do the final assembly, right? So you insert a number of elements and then you do assembly with flush, and then you add a number of elements and you do assembly with final. Okay, I wanted to just show you the created matrix. Let's see, finalize. Yep. So I'm just sabotaging the code just to get something quickly on the screen. Oh well, I am. I'm disabling everything after the matrix creation. Okay. And just with the, as with the vector case, oh, this matrix is rather large. I wonder if it has a, this code has, no, it does not have a parameter. Oh, and it doesn't show on what process stuff lives. Okay, so this was pointless anyway. Okay, let's do this exercise. So what is the exercise? There is a mat create routine. And then, so your part of the exercise is how do you get a vector that has the same distribution as the matrix? And then you duplicate it, and you have to fill in the parameters to do a matrix vector multiplication. Let's disable the second part. Okay, the code is again in the state where I where I started out. So make sure that that you disable exercise 2, where here the second test. Please disable that one with an if 0 and end if, and do the first part of the exercise. So given your matrix, find a vector that has the same distribution and then multiply the two together. Okay, I'll give you 5 minutes. Okay, were there any problems with this? Let's see, my sound is on. Yep. Okay, what was the question? First of all, your matrix is what kind of a matrix do we have here? Create. All right, what type of a matrix are we doing? MPI AIJ, okay, so that is it's distributed, so you want to have the row size, so row size, you're not interested in the column size, you're not interested in the global, and you're not interested in the global. And then setting the size of the vector is the row size, and let's see, decide for the global size. You duplicate that, and you set the vector to 1, and then you multiply a times x and the result into y. Everyone have something like this? See, if you want to know how routines like matvec work, oh, sorry, not matvec, matmult. See, there's a whole bunch of matmults, but you want to have this one. Matrix vector product, so matrix and vector go in, and the vector goes out. Interesting. What am I doing wrong? Let's see. First of all, there is an endif. Line 209. Ah, yes. And line 140, it complains. What line? Oh, error 140 on line 111. Oh, matget local size. That, of course, has only the row and the column local size. Still something missing, line 112. Ah. I love it that in Python you can have a dummy trailing comma. Okay, doesn't do anything. Right, anyway, so the code reports that it has a regression test, which came out correct. Right, so what this illustrates is that if you want to have a vector and a matrix that are compatible with each other, then you could, for instance, query the matrix and create a vector accordingly. No one had a problem with this? Okay. So you can retrieve the elements of a vector by vec get values, vec get array. In a matrix, you can do get row or you can do get array, but there is a trick here because, as I said, a matrix is stored in two parts. So if you want to retrieve a row, then PETSc internally has to create an array, copy those elements into it, and then later delete that thing again. So mat get row is not just a pointer redirection; it's actually a memory allocation, and so keep that out of computationally intensive loops. Yeah, that's the second part of matvec. There's a whole bunch more matrix types as I showed you. So, for instance, if you have multiple physical variables per node, then you can make a block matrix. Let's see, if you do semiconductor modeling, then it's P and N and something. Yeah. Please post something in Slack. I'm not that much of an application person, so give me something to work with. When in your field of science, do you ever have a grid with multiple physical quantities per node? Post something. GPU support. Yeah, so as I showed you in that list of types, there are things like mat Eijkhout sparse. Wow, Ben, 50 by 50 dense. That's a lot. So PETSc has, if you do a block matrix, then it has explicitly coded cases for, I think, up to 9. And after that, it just loops over it. But yeah, so this block matrix structure is optimized, at least for small cases. That's interesting. 50 by 50 with a Laplace. Right, so if you do it on a GPU, then you have to specify a type that this matrix lives on a GPU, and so you get things like Eijkhout sparse, meaning it's a sparse using the Q sparse package. All right. Yeah, if you want to have a portable code, then you could say create your matrix, and then the PETSc configuration leaves behind a whole bunch of variables. PETSc has this, PETSc has that, and so you can test if there is CUDA, then make it a distributed sparse CUDA matrix, otherwise just make it a distributed sparse matrix. I haven't had time to test this on Longhorn and see if the GPUs actually help. The RTX cards on Frontera do not help a lot, or at all. One GPU is better than one core, but Frontera has 112 cores per node, and there's no way you can beat that with a couple of GPUs. GPUs are great for machine learning and dense matrix operations. Okay, so I showed you that whole list of vector operations. Likewise, yeah, Han, Frontera is kind of a strange machine. So NVIDIA has the very powerful A100 or V100 GPUs that are very fast in double precision real. They're unfortunately also very expensive, and so we have a couple of those. But the RTX are not great at double precision. They are better at single precision. So we sort of say that those are the machine learning GPUs. But any type of GPU really doesn't help a lot if you do sparse matrix operations. So the PETSc guys used to say that a GPU may give you a factor of 2 or 3 improvement, but that was when processors had just a few cores, and these days Frontera has 112 cores per node, and Lone Star 6 has 128 cores per node. So yeah, I'm not sure that I think we have 2 RTX cards per node. Maybe if you're doing machine learning, they can beat the regular CPUs, but definitely not for sparse operations. Sparse operations and GPUs, GPUs don't really help a whole lot. Okay. Oh, absolutely. Yes, I'm completely misspeaking. I had the number 56 and two sockets in mind. Yeah, you're absolutely right. It's a 28 core chip, and times 2 is 56. Entirely my mistake. 56 cores per node. Yes. Sorry. But still, that is an awful lot of computing power. And with a GPU, you have the fact that they are the GPU memory and the CPU memory are is it PCI X or something? Anyway, the GPU cannot immediately access the PC memory, and so sorry, the CPU memory. Anyway. I don't use GPUs a lot, so I don't have a full picture of where and when it works. Okay, you have all the vector operations, you have matrix operations. So in this exercise just now, you saw the matmult, which is a matrix times vector becomes vector. The matmult add, which adds the vector to an existing vector. Transpose add, operations on matrices. So if you do partial differential type of operations, then you don't need a whole lot of matrix operations. Most of the time you're doing matrix times vector, but PETSc has a bunch of matrix operations. And in particular, so yeah, mat PTAP. So you multiply the same matrix with something from the left and from the right. Does anyone know why you'd want to do that? I'm sure there are multiple scenarios, but I can think of one immediately. Okay, so I multigrid. So I showed you that you can do a vec view, and likewise there is mat view. And you can put this in your source as a mat view or vec view call, or you can do it with an option. So viewers, which you've now only seen as a way of doing an ASCII rendering, are actually very general. So viewing is viewing the way you've seen so far is viewing the standard out world, but there is a whole bunch of viewers. So for instance, you could do view draw, which if you have an X term attached, and I don't have that right now, then you can get a drawing of your matrix, the sparsity pattern. Writing a matrix to file is a viewer. So it's so there is a general concept of viewing. So for instance, terminal output, binary output. You can also use a viewer to load a matrix. You can view through a socket, so you can pump your matrix to MATLAB. In this particular example, I create a viewer with type VTK, which is a graphics package. And now if you view the matrix, then it goes to a VTK file. Even if so, let me remark on the fact that you can view a matrix to HDF5, so that is very useful. Then you have it in a portable binary format that can be accepted by other packages. I seem to recall that VTK can read an HDF5 matrix, but anyway. Okay, so I've shown you a bit about sparse matrices. In certain applications, you have something that, in terms of your application, is a matrix in the sense that it is a linear operator, but you don't actually have a data structure for it. What you have is a routine that computes the action of your linear operator. Let me know in Slack if that appears in your application, that you don't have a stored matrix, but you have a routine that computes the action of it. So PETSc deals with that through the so-called shell matrix. And you can do a mat create and then set type shell and then set sizes, or you can do in one call mat create shell. So if you have a matrix that is operationally defined, let's put it that way, then how does PETSc know how to multiply with that matrix? Well, that goes like this. You write your own routine, and it has to look like a matmult. So matrix and vector in, vector out. So you write your own routine, and then you tell PETSc, okay, my shell matrix has a matmult operation, and here is the function pointer. And now if you do a PETSc iterative method, then inside it, it has to do a matrix multiplication. And now even if you have a shell matrix, then PETSc knows how to do the multiplication, namely by retrieving the pointer to your routine and using that. Okay, no one is saying anything in Slack, so apparently this is not a scenario that appears in your applications. If you're doing a Newton method and you're too lazy to compute the Jacobian, you can do a Jacobian by doing two function evaluations and differencing them. Okay, so that's you can do that with the shell matrix. If your matrix needs extra data, then you can put it in a structure which you pass as an opaque handle. In Fortran, unfortunately, opaque handles don't exist, and so you have to use a common block or a module. Yeah, here's an example. Sometimes you want to take a submatrix of a matrix. There are two different routines for that. Mat get submatrix takes a matrix, and if the matrix is distributed, then the submatrix is also distributed. Let's see, how does this work? You have your matrix, and I have not discussed the IS data type yet. So we'll see that later. So this indicates what part of the matrix, which rows and columns you extract. If you use the mat get submatrices call, then the submatrices are stored locally on a process. So because they come from all over the place, this is a collective routine. But so you can give every process separate rows and columns to extract. I'm just mentioning a whole bunch of things that you can do with matrices. Some of them may apply to your problem, some don't. Let's see, mat partitionings. So if the scheme of dividing a matrix by block rows is too limiting for you, then you can... Oh no, sorry, that's an application ordering. A mat partitioning is a different way of distributing a matrix, including renumbering it. So there are these packages like Eijkhout and Parmetis that do grid partitioning. And so if you have a grid partitioner, then you can use that to repartition the matrix accordingly for load balancing. We are creeping up on the top of the hour. Let me do something about index sets, and then we break, and then in the afternoon I probably need only one slot in the afternoon to talk about iterative solvers and grid manipulation maybe. So let me get a short topic out of the way. So if you deal with unstructured sparse operations, sometimes you need to do things like collect the boundary elements. And so you have to have a way of talking about indices, and you have to have a way of saying, okay, now collect them together. If you have to write this yourself in MPI, it's an unbelievable hassle. So PETSc has the following. It has the concept of a vex scatter. And a vex scatter is a mapping from one vector to another. And so you can rearrange arbitrary data as long as it's stored in vectors. So for instance, if you have a two-dimensional data set and you have a vector that corresponds to a row-wise partitioning, and you want to change that into a vector that corresponds to a column-wise partitioning, then you can do that with a vex scatter. So you create your vex scatter, and then again there is a begin and an end where you say, okay, take this vex scatter, apply it to an input and an output vector. Is it inserting or adding? And are you running the scatter forward or backward? Okay, so this is a way of mapping from indices in a vector to indices in another vector. Completely general. Okay, so the vex scatter is made from two ISs. What is an IS? An IS is an index set. So you can make index sets in a number of ways. Let's see, a general index set is you tell it, okay, this is 25, and then you give it an array of 25 indices. and then it copies it into your IS object. You can have a strided, so this many starting here with this stride, or you can have a block size, and then how many and where do the blocks start. So it's a little like MPI derived data types. And if you want to do complicated stuff, you can do the union of index sets. You can difference them. If an index set is a permutation, you can flip it. So there's a whole bunch of routines. Let's see. So, okay, like I said, if you want to go between ordering, so for instance, you have what is this? 2 processes and a total of 12 indices, 0 through 5, 6 through 11, and now you want to flip them so that process 0 gets the even and process 1 gets the odd ones. So these are 2 distributed vectors, and you want to shuffle them. So how do you do that? If I am the even, if I'm process 0, then I want to get the even indices. So I make a strided from 0 to 2. And if I am process 1, I make a strided from 1 with steps of 2. And then you create a scatter where you say, okay, this is what my input vector looks like, and these are the indices. This is what my output vector looks like, and you don't need the indices because they're going to be contiguous, and you call that separate, and then you do the scatter, and yeah, okay, so you can do an exercise about that if you want. Anyway, so for certain applications, you sometimes want to rearrange vectors or do stuff like gather a boundary, and so that's what the vec scatter is for. Yeah, there's some duplicate stuff here. Okay, let's take a 1 hour break until 12:50 approximately, and then after the lunch I will go over mostly linear system solvers and a little about how to create linear systems if you have a Cartesian grid. Okay, break until 12:50. Back from lunch. Okay, so let's start up an IDEV session, which can run for maximally 2 hours. That should last me to the end of this tutorial, probably. Am I sharing screen yet? No, I am not. Now I am. CD exercises, PETSc. Okay, so in scientific computing, the matrix vector product is often the most important operation. Why? Well, if you do a forward stepping, explicit time stepping method, then clearly you're doing matrix times vector all the time. If you are solving a linear system because you're doing implicit time stepping or steady state or inside a Newton step, then you're solving a linear system. But how do you solve a linear system? Okay, you can do that two ways. You can do Gaussian elimination, or you can use an iterative method. And iterative methods, again, are matrix times vector. So even though you're solving a linear system, matrix times vector is a normal part of that. So that is what PETSc is mostly built on, linear system solving by iterative methods. Why do you do that? Gaussian elimination is sort of predictable. You sort of know how fast it works. Except of course, if you have a sparse matrix, yeah, how much fill-in do you get? Difficult to estimate. Iterative solvers, on the other hand, do not use Gaussian elimination. They use successive approximations of the solution. So you start with one approximation, you get a better, you get a better, you get a better. For very badly conditioned linear systems, convergence may not always be guaranteed. If it does work, then it can be much faster and more memory efficient than Gaussian elimination. The basic operation is that in each iteration you multiply some intermediate vector to get an update, and you use that. To speed up this process, you need something called a preconditioner, which is an approximation of the matrix or an approximation of the inverse. So the way PETSc is set up, all linear systems are iterative. Even the Gaussian elimination type direct solvers, they are basically an iterative method that stops after one iteration. So you have the linear systems, we have the iterators, we have the preconditioners. I will talk about command line options, and there is a lot that can be done there. And then some topics like convergence tests, monitors. Okay, so first of all, KSP stands for Krylov space. It's probably an abbreviation that was decided more than 20 years ago and we're stuck with it. So a KSP object is a linear system solver. And so you create the KSP and you destroy it in the end when you're done with it. A linear system involves the coefficient matrix, the right-hand side, and the solution. So you set the operator of the linear system. Actually, you set two operators. Why? Well, the first one is the system that you actually solve, and the second one is a potentially different one that can be used to construct a preconditioner out of, but usually you just give the same. And then you do a solve call, KSP solve, which applies the solver to the right-hand side, giving a solution. Okay, so there is a whole bunch of KSP types. You have to set the type solvers. For instance, GMRes. I don't know how much have people here in the audience come in contact with iterative solvers. Any idea what GMRes is about? Can you name other iterative solvers? CG, which stands for conjugate gradient. BiCG stab, very good. That's a, yeah, biconjugate gradient stabilized. That's actually a very good one. BiCG stab is one that I recommend as a sort of a default. I think PETSc actually uses GMRes as the default, which is generalized minimal residual. So you can set your KSP completely from, by the way, BiCG stab was written by a fellow countryman of mine, and the paper that he wrote about it was, by one metric, the most cited math paper of the 1990s. Henk van der Vorst, but that aside. So you can specify your solver completely in your source code, but there are so many possible options and you may want to experiment with them that it's a good idea to specify options on the command line. And so when you specify enough of your solver in your source, you have a call to KSP set from options. That's in between the create and the solve call. And any options minus KSP are at that point applied. So for instance, if, as Hans suggested, if you set the type to KSP CG, but then you change your mind, then you can do on the command line KSP type GMRes, and so it switches the type. So you can experiment with what type works best for you on the command line. And then if you have decided on a GMRes solver, that thing itself has options. So usually GMRes is used as a restarted method. So then there is an option KSP GMRes restart. And once you put your solver together, you may want to do KSP view, and that will print out all your options. Okay, so there is the KSP solve call. This is slightly deceptively named because it may not necessarily compute the solution. What KSP solve does is it iterates for a while until either it has found the solution, or it runs out of iterations, or it decides that it's a runaway process where the error only increases and it stops. So KSP solve has no guarantee, and so when KSP solve returns to you, you should ask it, okay, KSP get converged reason, what is the reason that you stopped iterating? And it gives you a number. Anything positive means it stopped. It means it converged. And anything negative means divergence or maximum number of iterations reached. And then if you have that reason, then there is an array of strings that gives you in a readable form the reason. So suppose that KSP get converged reason tells you that positive number, yes, it stopped with convergence, so successfully reached the solution. Then you can ask, okay, get iteration number. How many iterations did you run? Okay, so here is the here's a bit of sample code. Get converged reason, get iteration number. If reason is less than 0, then print failure to converge after so many iterations with reason. And otherwise you say number of iterations to convergence is whatever. So this also illustrates that PETSc is a toolbox it's not one massive solve a linear system call that guaranteed gives you the best solution. It's a toolbox. You set all your options, you call a routine, and then you have to ask, did it actually converge, and all that. Okay, so KSP, create, set operator, set type, and then solve. That's easy enough. Now, unlike Gaussian elimination, which mostly depends on the structure of a linear system, so the sparsity structure, iterative methods don't care much about sparsity structure. They care about the spectrum of the matrix, so eigenvalues or singular values. And there are some theoretical results in certain cases that the number, for instance, for conjugate gradient, the number of iterations is proportional to the square root of the condition number of the matrix. Does anyone know what a condition number is? What does a condition number depend on? If I have a Laplace equation with a certain mesh spacing, what is the condition number? Type something. Anyway, so it depends on the spectrum. Yep, condition number is the ratio of max eigenvalue over min, or in general singular value. If you have a Laplacian linear finite elements, what's the value of the condition number, or what's the order? So it depends on the spectrum, and so if you can find a matrix that is close enough to the if you find a matrix M that is close enough to A, then you can precondition this system to get the spectrum a little more compact. After all, if M equals A, then M inverse A is identity, and so the spectrum is just 1. But in general, that you cannot find the inverse, then you would have been done. But preconditioners try to tame the spectrum a little. Okay, so in every iteration you have to multiply with the matrix. So in every iteration you have to multiply with A and solve with M. And so you need to find an easily invertible approximation of your matrix A. Okay, I don't see any further contributions in Slack. If you have a Laplacian in any number of dimensions with mesh spacing h, your condition number is h to the minus 2. And so for 2 dimensions, that means that the condition number is proportional to the matrix size. And so and then you have to know that the number of iterations is proportional to the square root of the condition number. And so in 2 dimensions, if you make the mesh spacing half as, twice as fine, if you divide the mesh spacing by 2, your matrix blows up by a factor of 4, and so your number of iterations goes up by a factor of 2. Okay, so larger matrix, more iterations. But the preconditioner serves mostly to squeeze the proportionality factor. The preconditioner is constructed once and then applied in every iteration. So some preconditioners are very expensive to construct, but they lead to a low number of iterations. So it's a trade-off. Simple preconditioners are easy to make. For instance, the diagonal of the matrix is a good approximation to the matrix and takes 0 effort to construct, but it may not it'll probably only give you a small factor of improvement. Right, a subtle point. The conjugate gradient method only works for symmetric matrices, and even if A and M are symmetric, M inverse A is non-symmetric. However, conjugate gradient does something with the change of inner product, which makes M inverse A symmetrizable, and so it still works. Anyway. Yeah, so that's about preconditioners. And so preconditioners are just about are one of the few PETSc types that do not get created explicitly. If you create your KSP, then it automatically has a preconditioner built in. And so with KSP get PC, you dig it up, and then you set its type. Okay, PC none is kind of pointless. It means use the identity matrix as preconditioner. So PC Jacobi is use the diagonal of the matrix as preconditioner. ILU is incomplete LU. I'll say something about that in a minute. But the more interesting ones are additive Schwarz and block Jacobi. And then there are a couple of multi-grid preconditioners, and in fact, there's a whole bunch. And just like what I said about command line options, the same goes for preconditioners. So the iterator, you specify it with KSP type, and then sub options. For the preconditioner, you do PC type. For instance, if you do ILU, and then because it's a factorization preconditioner, you can say, okay, how many levels factorization? So there's a whole bunch of command line options. Let's not talk about this. Yeah, so in elementary numerical analysis class, you may have learned about Jacobi, SOR, ILU as iterative methods for linear system solving. Does anyone know what the UT connection with SOR is? I don't see him mentioned that much anymore. SOR was one of the big things 70 years ago when this whole field was invented, and SOR was invented by David Young, who for practically all of his career sat on the 13th floor of RLM. He died, what, 20 years ago or so? So these days, these methods are not used as independent iterative methods. They can be used as preconditioners, but methods like block Jacobi, additive Schwarz, they are quite hard to code, but it's a good thing that in PETSc it's just one option, and so it's very easy to use. So there's no reason not to use a complicated method like additive Schwarz. Okay, so let me just say a couple of things. Things like Jacobi, Gauss-Seidel, SOR are all preconditioners that are formed from the matrix elements, and so they take zero effort to construct. So you split your matrix as a diagonal lower and an upper part, and then, for instance, the Gauss-Seidel preconditioner is the triangle of diagonal plus lower part, and it's very easy. So it's trivial to construct, and it's very easy to solve a linear system with a triangular matrix, right? Everyone knows how that goes. Forward sweep. Likewise, SSOR is forward sweep and backward sweep, but again, using the matrix element. So these are very simple, cost absolutely zip to construct, but they're kind of limited in use. Now, intermediate option is so-called incomplete factorization preconditioners. So A equals LU is a Gaussian elimination, reduction to upper echelon, row upper echelon form or something. Can't get my words straight today. Anyway, so you split your matrix as the product of a lower and upper triangle. Both of them are easy to solve with, but they suffer. If you make the exact factorization, you get a lot of fill-in. So people, starting when 1970s or so, started considering incomplete factorizations. So if you do a Gaussian elimination, that worked as follows. In step K, for all I and j, you update Aij with this. This is basically the simple formula for Gaussian elimination. Gaussian elimination is a triple loop, and this is the body of the innermost line. So the problem here is that you may have locations where Aij is originally 0, but you update it with something non-zero. So that is the definition of fill-in. Now, an inexact LU does the following. It says only if the matrix element was originally non-zero, then you do the update. Or you can do it in levels. You can say, okay, if the matrix element was originally 0, then you update it and you mark that as level 1. And now you only, and then you recursively get level 2, 3, and you only allow this many levels of fill-in. So that's an incomplete factorization preconditioner. PETSc has those two. In fact, it has incomplete Cholesky for symmetric and incomplete LU for non-symmetric. And there are a couple more things you can do with that. I'll spare you that. Okay. Yeah, so both LU and things like Gauss-Seidel are based on first solving a lower triangle, then solving an upper triangle. What is the problem with that? We are being parallel, right? Okay, so what's the problem? Communication, yes, but that's more a programming headache, figuring out how to communicate. There is a more serious problem. How do you do a forward sweep? You solve the first component, then the second, then the third, then the fourth, then the fifth. Okay, now you have 1,000 processors. Recursion is never good for parallelism. You want to have as many independent operations as possible. So, okay, so you have to be really clever to do an ILU in parallel, but in the straightforward formulation, it's just not a good idea to do that in parallel. Okay, hold that thought for a minute. Now, the block-Jacobi and additive Schwarz method do the following. So you have your matrix, and usually it has a banded structure. And now you say, okay, I have 3 processors, and I'm just going to throw away the elements that connect one processor to another. So now you've approximated your band matrix with a block diagonal matrix. And of course, it's not a perfect approximation, but it could be a reasonable approximation. So, okay, but now, so now solving with, so this is your original matrix A, which is banded, and your matrix M that you use as a preconditioner is block diagonal. Okay, but now how do you solve a system with your matrix M? Well, processors 1, 2, and 3 solve independently with their block. Okay, but now now you can use the factorization preconditioners as a way of doing that local block. Okay, so incomplete factorization preconditioners are hard to do in parallel, but if you first make your problem into a bunch of independent problems, one per process, then using it there works fine. Okay, so this is the block-Jacobi method. The additive Schwarz, I didn't have a good picture of, and no time to make one. In that case, the blocks are actually a little larger and they overlap. And so some variables get solved twice, and so you need to add them, average them, something. You have to reconcile it somewhere. But additive Schwarz is actually is theoretically better. Anyway, so both methods, block-Jacobi and additive Schwarz, give you a preconditioner that is fully parallel over the processors. And so you only need to do a local solver. Okay, so now how do you do that? Okay, so you have your block-Jacobi preconditioner, and then you get the sub-solvers. So that's an array of solvers, and then for each solver you say, okay, on this block do a GMRes, and then you extract the preconditioner from it, and you say, okay, put an ILU on that block. Okay, this is a tremendous headache to program. So here it is, here's where PETSc's command line options really shine. So after you say PC type block-Jacobi, you can say, okay, now the sub KSP type is GMRes or CG or whatever, and the sub PC type is whatever. Okay, so instead of this block of complicated function calls, it's just a couple of simple command line options to set your complicated solver. Okay. Is everyone back on Frontera? Is everyone on in an IDEV session? This file should be complete by itself. Yep, and if you IB run KSP, then it should solve the linear system. Okay, so in this exercise, I want you to play with command line options. Let's see what happens in this code. KSP.c. So it makes a 5-point matrix. Yes, there is a flag dash unsymmetry. So you can make your matrix more or less unsymmetric. Let's see. Oh, and there is a minus n, so it's a 2D Laplacian. So minus n is not the matrix size, but it's a domain size. So if I run this minus n4, then it's size 16. Let's see, let's view the matrix. It should be size 16. Yes, it is size 16, so this is a Laplacian. And if you do unsymmetry 1, then it gets a, now let's 0.5. See, then it fills in elements above and below, yes, above and below the diagonal with size 0.5. So this is a code that is set up for just doing simple experimentation. Question: does it mean that block Jacobi in parallel is to apply ILU for each block diagonal matrix? Okay. So on the left you have your matrix, and then you make your preconditioner by first removing the connections. So this is for 3 processors. And so now you have 3 blocks that can be independently solved. And so on the way a block Jacobi is set up is that every process solves its own block independently. Now, how does a block solve it? So the subsolver is by default, do not iterate, but just apply the preconditioner once. So it's basically, it's like a 1 iteration iterative method. And that iterative method has a preconditioner. So in your block Jacobi, you have your subsolver, which is pre-only, means just apply the preconditioner. So iterate 1 iteration. And then it has the sub preconditioner, and that is whatever you specify. So each process applies ILU on its local block. Does that explain it? So you do a single pass of ILU on the top block, middle block, and last block in parallel, because you have 3 processes. Okay, great. Right, so there's a code that you can experiment with. It creates a 5-point matrix depending on the minus n and depending on the unsymmetry parameter. ./KSP. I don't quite like how this works. So if you run your code with help, you get all of the possible PETSc options. And no, I didn't even document the options for this code. So, yeah, okay, never mind. PETSc initialize. KSP minus n domain size minus unsymmetry make KSP IB run minus N1 to prevent KSP help. Okay, see that I added an information string to the program, and so the help prints out my information string. So you can leave a note to yourself explaining what the program does. Yeah. Okay, so this is the default. Domain size is 100, so the matrix is 10,000 by 10,000, and that takes 147 iterations. Do you remember what I just told you about? Oh, let's see how it did that. So I run the code with KSP view, and now when it does the setup of the solver, it prints it out. So this is a conjugate gradient. It runs for maximally 10,000 iterations. It looks for a relative convergence of this, absolute convergence, and it will diverge if the error goes up by 10,000. All of this can be changed with settings, and the preconditioner is Jacobi. Yeah. Okay, so you can see what solver it uses. So on a, this was size 100. It takes 147 iterations. If I take size 200, what's the number of iterations going to be? You remember from my stuff about condition numbers a minute ago. Four times, yeah, the condition number goes up by 4, but the number of iterations goes up by the square root of the condition number, so it's actually double. But thank you for piping up. You were in the right direction. Okay, so that works. Oh, and if you want to see how it did that, then there is KSP monitor. So that gives you the convergence history. Let's pipe that through less. So the arrow starts out at 5 times 10 to the 1. It goes up, but after a while then it comes down again. And so it looks for a total reduction of 10 to the minus 5 from the original. Okay, the error is not monotonically decreasing. It can easily go up initially. The theory of why it does that is very complicated and very incomplete. Okay, so your code can be controlled by -n and by unsymmetry, and let's see, how many hints am I giving you? Not enough. So let's see if I go to the man pages, KSP set type, KSP set type, does it give me a list? No, unfortunately it doesn't. How do we quickly do this? Echo $PETSc dir. Okay, Emacs PETSc dir include PETSc ksp.h PETSc pc.h. Where is the list of all preconditioners? Oh, PETSc PC types. No, not this. Okay, so here you have a number of options. So I'm going to leave you alone for 10 minutes or so and experiment a little. So run the code with various sizes, various amounts of unsymmetry, and then try to, so by default, the KSP type is CG. Conjugate gradient only works for symmetry. So what happens if you make your matrix too unsymmetric? So here are a couple of options that work. GMRes works for non-symmetry, and ignore all the variants. And here you have BiCG stab that works for non-symmetry. And then you have what ILU as a try something with preconditioners. See which ones work. Actually, so try something along these lines. Run it with KSP type. You pick that one. See what happens if you try PC type ILU, but really try PC type block Jacobi, and then sub PC type one out of that list. Let's see, how can I do this? I want you to be able to see this line. See this, and how did I do that? I didn't know my terminal program could do that. Okay, I hope this is all visible. So I'll set a timer for 10 minutes, experiment a little. Oh, and also remember here on slide 92, this is also something you could try, KSP, GMRes, and then tinkering with the restart length. Okay, so experiment. What works, what doesn't work? If it works, does it converge slower, faster? We're actually not printing out run times, only numbers of iterations, but yeah, play with it. I'm setting a timer for 10 minutes. If you have problems, post in Slack. What is a good range for the unsymmetry? Yeah. It's sort of modeling a convection diffusion, except that the mesh size is rolled into the parameters. Try both less than 1, so between 0 and 1, and try large values, but yeah, just see what works. Is anyone reaching any conclusions yet? Post something in Slack if you make interesting observations. Really difficult to converge for unsymmetry more than one. Where is my... Oh. Let's see, so IB run KSP. Thank you. Let's see, unsymmetry 5. Okay, first of all, let's use the default size. And it converges. Still converges, but takes more iterations. And at some point, So, okay, diverges, interesting. I thought CG would have converged with detecting a okay. So here you get if the unsymmetry gets too much, then it says it diverged for iterations, meaning it hits the maximum. If the unsymmetry gets even more, then it says diverged with divergence tolerance. It keeps being divergence tolerance. At some point, I thought it would detect, okay. I thought it would detect that there is an unsymmetric preconditioner. Oh, no, or an unsymmetric linear system. Anyway, so yeah, let's so if the unsymmetry is too much, so one reason that it doesn't converge is that conjugate gradient is only guaranteed to work with symmetric systems, or symmetric positive definite systems actually. So if we change the KSP type to something, interesting, diverge with nan or inf. Okay. I'm not sure what to think of nan or inf, but it's going very wrong. But we're still using a very simple-minded preconditioner. So instead of PC type, I think it was Jacobi, right? KSP view. Yes, it's using a Jacobi preconditioner. So let's do PC type block Jacobi. Diverged breakdown. Additive Schwartz. Yay, and now it works. Okay, so you see that depending on your problem, you may need to tinker with what solver to use, what preconditioner, what. Right, so this is additive Schwarz, and now if you do KSP type, so additive Schwarz is very closely related to, where was that picture of block Jacobi? Okay, here's that picture. So additive Schwarz is like block Jacobi but with slightly overlapping blocks. Why do overlapping blocks help? Additive Schwarz is actually interesting. It was invented by Mr. Schwarz in 1890 or something, when computers didn't exist, but he used it as a way of proving that so in those days you could solve Laplace's equation on a square or on a circle. Now what if you have a circle overlapping with a square, and he showed that by solving the one, then using that as boundary condition for the other, and etc., etc. So iterating that you would arrive at a unique solution. So he used, this is actually a theoretical device for proving the uniqueness of solutions. Anyway, additive Schwarz uses overlapping blocks. So you lose a little less of the thrown away connections, and hey, so it works a little better. Now, okay, so the, what? PC is, no, what am I doing here? Okay, PC type is ASM, is additive Schwarz method. And then the sub-solver is just apply the preconditioner, but the sub-preconditioner is ILU. Okay, now sub-PC factor levels 5. So it converges in 59 iterations, right? Oh, I mistyped. Okay, so if I make my incomplete factorization a little more accurate by allowing multiple levels, then it converges faster. It went from 59 to 20. Now let's see if this is robust, if what happens if I yeah, okay. Okay, so if this was my convection diffusion problem with a heavy bias towards the convection part, then using BiCGS with additive Schwarz and several levels of ILU fill-in would probably be a reasonable preconditioner, a reasonable solver. Okay, and you wouldn't believe how much headache this would be, this experimenting, if you had to do it with function calls in the source. Can I explain the sub-PC levels? Yes, I can. So, okay. So an LU is, yeah, update all your elements. I hope this formula makes sense. You have the kth elimination step, and in each step you update your under matrix by, yeah, that's the formula for Gaussian elimination. Now, if you do an incomplete LU, then you say, okay, I'm going to preserve the sparsity, so only if the element was non-zero, then I update it. And otherwise, if there was originally a 0, then I just throw away the update. Okay, so this is also known as a level 0 ILU. A level 1 ILU is you would allow fill-in if the original elements were on level 0. So then the fill-in is level 1, and you would only allow fill-in the coming from level 1 elements. If you allow fill-in from level 0 and 1 elements, then it's a level 2 preconditioner. So yeah, the more levels, the more fill-in you allow, and the more exact your preconditioner becomes. Right, so an exact factorization would be a level square root n or something preconditioner. Okay, so I allow more and more fill-in, thereby making the preconditioner more exact, less inexact, I guess. Yeah, so depending on what your problem looks like, you have to tinker with the preconditioners. There was a question about the hyper preconditioner, 5 orders. Let's see what we can do there. So hyper is a strange case because hyper is a completely independent package out of Lawrence Livermore, I think. It converges, but Ben was saying something about the... Okay, Ben, you'll have to clarify that. What were you seeing with the hyper preconditioner? It starts out higher, does it? Oh, yes, absolutely. Yeah, why is this? I don't know. Different preconditions behave differently, and yes, you can say if you start out with a higher error, does your ultimate result have the same sort of accuracy? Yeah, that's always a tricky question, which is why PETSc has different convergence criteria. Higher level requires more. Okay, Han, yes, absolutely. Good point. To come back to the factorization levels, if you do more levels, then you get fewer iterations, but it's also more work per iteration. So there is a trade-off, except of course when come on. Oh, okay, so it could be that for a low number of levels you don't get convergence at all, and so there is a minimum number of levels, but no, here it looks like any number of levels converges. So there is a trade-off. Maybe more levels will give you a reduction in runtime. Maybe it will actually increase the runtime because you have fewer iterations, but each iteration is more expensive. Okay, so I'm not sure if there is a quicker way to... Okay, so this ran in 8.8 seconds. that was the 1 level, and 5 levels. So let's see, what was it? 5 levels in 130 iterations. Okay, so 5 levels gives you a quarter the number of iterations, but the time goes down by 2. So there is a gain. The reduction in iterations is more important than the increase in work. So okay, but yeah, good point. Okay, so now you've experimented with different solvers. I hope you get the notion that there is a lot of possibilities, and yeah, you have to find what works for your problem. ILU. Okay, so I was using the default tolerances. So RTOL is a relative decrease in residual norm. ATOL is absolute decrease. DTOL means divergence. So if the error goes up by that much, then you decide to call it a day. And the maximum number of iterations, etc., etc. You saw KSP monitor, and there is a monitor true residual. You can have your own convergence tests and your own monitors. So if for whatever reason you want to print out a certain component of the residual in every iteration, then you can do KSP monitor set and you give it a routine, etc., etc. Convergence tests, you can write your own convergence test. There is a whole bunch of advanced options. Yeah, PETSc is, I guess it's coming up on about 30 years old. I first learned about it in the, mid-90s or something. So yeah, it may be almost 30 years old. And it really incorporates the sum total of all numerical analysis knowledge of anything that's happened over the last God knows how much time. Anyway, so there's a lot of options that you may never come across. I'm just mentioning a number of the most common ones. Null spaces, if you have a singular matrix and you want to find the solution orthogonal to the null space, then blah blah. Matrix-free solvers, we already did that. If you, right, you can create a matrix out of submatrices this way, but really, if you have multiple unknowns per grid point, then it is better to make a block matrix. And sometimes the multiple unknowns have different characteristics, and so you want to solve them differently. And so that's a field split preconditioner, where you apply one preconditioner to quantity 1, then another one to quantity 2, quantity 3, etc. Just mentioning that it exists. Oh yes, of course, the Stokes equation is a great example for that, because you have a saddle point and you need to be yeah, field split. PETSc has a multi-grid solver facility. Okay, so who was it? Ben tried the Hyper preconditioner. Hyper is an independent package, kind of a competitor to PETSc. It is less developed in some senses, but it has a number of very sophisticated preconditioners that PETSc doesn't have. And so the PETSc developers decided to incorporate Hyper into PETSc, and so now you can use the Hyper preconditioners. But so there is not one Hyper preconditioner. You have to say PC type Hyper and then PC Hyper type. And so there are 4 different Hyper preconditioners, all of very different character. But they do things that some of the PETSc preconditioners cannot do. So it's very useful to know about the existence of this. Okay, direct methods. So yeah, the way PETSc works is KSP solve sort of presumes an iterative method, but you saw in the subsolver that there is a KSP pre-only, which means iterate by only applying the preconditioner once and then calling it a day. So it's like a one iteration preconditioner. And that is in fact how Gaussian elimination in PETSc works. You declare an LU preconditioner, so a full factorization, and then you say, okay, my KSP type is only do the preconditioner. The preconditioner is a full factorization. Okay, and PETSc does not have parallel LU factorizations built in, so you have to tell it from what external package it comes. And mumps, which I think is French out of Inria, has a distributed memory dense LU. So, yeah. Okay, I am going to take 5 minutes to catch my breath, and then I will do section 7 and a couple of minor topics, and then we're done for the day. Okay, 5-minute break. Okay, so in some of the lab exercises you saw, there was a routine for creating a matrix, and it did that by filling in the matrix elements. In fact, if you, whoops, sorry, my keyboard hanging from the other computer. Here, this routine 5-point matrix. So what this routine does is it actually does not iterate over the matrix, it iterates over the two-dimensional domain, and then it says that, so I and j iterate over the domain, and that gives you a global variable number, and then you test is that mine or does it belong to someone else? And so then you set the matrix elements. For instance, the diagonal element is I global comma I global with a value of 4. Okay, so I'm iterating over the domain, and for each domain point I set the matrix elements. If you have a Cartesian domain, then PETSc actually has tools for making this sort of stuff a little easier on you. DMDA, DM stands for, I don't know, I was talking to one of the PETSc developers, and he says it stands for deeply mysterious. DA is a distributed array, and DM is a distributed matrix or something. So a DMDA is a data structure for kind of corresponding to the physical domain of definition. So even though it's an array, it's not a matrix. And so stencils, like you can declare a star or a box stencil. You can say something about the stencil width, ghost regions. Okay, so what is a DMDA? There are separate routines for create 1D, 2D, 3D. And you create your domain of definition on a communicator. How are the boundaries treated? No, is it no boundary, ghost, periodic? Type is this a box or a star stencil? Size of the Cartesian domain, and so this is only global in x and y direction, and corresponding how many processors do you want to have, and you can leave that up to PETSc. Is there more than one physical quantity per node? What's the width of your stencil? And then some stuff that you can better leave as a default, and from it you get your distributed array. And then you can, of course, this needs to be a little better formatted. Sorry, these slides are too new. So corresponding to a DMDA is the grid information. So once you define the global grid like that, then each process knows, each process has a subdomain. So PETSc tries to cut it as much as possible in low aspect ratio. as square as possible subdomains. So you don't specify that explicitly, or you don't have to. And so every process knows, okay, my subdomain starts at, why can I? Somehow I cannot select this text. What's wrong here? Okay. No idea. So the XS means the starting point of X, Y, Z, and then the XM, YM, ZM is the extent of my subdomain. Now, because your stencil has a certain width, there is also the halo or ghost region around it. And so you have the GXSYSCS, which is the including ghost points start of my subdomain, and then the GXM, etc., is the extent of my subdomain plus ghost. Sorry, I've been updating the book and I think the slides got sort of left behind. Okay, so you have this grid and a stencil on it, and that leads you to this structural information. To use that, okay, there are two concepts. There is a local vector and there is a global vector, which is not defined in this. A global vector is a vector in the traditional sense, so cutting the total space into partitions. A local vector is different. Hold on. When did I last update the book? I wonder if this is better in the book. PETSc grid support. Okay, so what do I have here? I have a 100 by 100 domain, and I run this over 4 processes. And so each process, so process 0 reports that it has subdomain 0 to 50, 0 to 50, except that because of the halo, it has 0 to 51, 0 to 51. Process 3 has 50 to 100 by 50 to 100, and because of the halo, it actually has 49 to 100, etc. Okay, so that's what you get out of the grid info. Okay, what can you do with that info? If you have the, where can I get your book? Same download location that that you already have. So the web corral tag, it's at the top of the Slack channel. Link to slides and textbook. Imagine that. Probably the best book on the market, and it's for free download. Yay. Okay, so out of the grid info, each process derives what is my starting point and what is my extent. And so now you can write code where you put stuff in the vector of that domain. So you loop over I and j, and then you do some action on point I and j. Okay, what do you do? Okay, so if you have a DMDA grid and you have a vector that is commensurate with your grid, and then you extract the array from it, you get the situation that with this sort of 2D indexing, you get access to the local component in the vector corresponding to local I and j. So you do get array, you iterate over your local domain, and you do something with that vector, and then you restore it. So obviously this can be used to set the right-hand side for a linear system. Okay, now suppose you want to do something like you have one of these situations where you need to apply a gradient to the right-hand side, or yeah, so you have a right-hand side that itself is Laplace of something. Okay, how do you do that? The Laplace operator has this ghost behavior. So what do? Okay, you have a local vector. I hope this is readable. I have a big monitor here. I'm not sure if you're watching it on a laptop. I hope this is readable enough. So dm get local vector is a vector that on each process has the subdomain plus the ghost region. Okay, so xy was the vector that here. Xy is a normal, nicely distributed vector. Now I have a ghost vector that is local, meaning that it has the ghost region. I call global to local, so my vector xy gets inserted with ghost points in the ghost vector. Then I get my array from both, and I do something on the xy array to create the Laplacian in the ghost vector, and then maybe I copy it back. And so here's the code that does that. I iterate over my ij domain. I test if I'm not on the boundary. Why is that a double test? Not sure. Anyway, if I'm in the interior, then I can compute the Laplacian. Okay. Yeah, there are various reasons why this is a little better than inserting the matrix elements yourself. It's definitely a little easier to write because PETSc takes care of this mechanism, global to local, creates a vector that has the ghost, where each process has the ghost region, and so you can do a Laplacian on your right-hand side. Okay, so now you've made a vector corresponding to your grid, but how about the linear system? Okay, so for that we have a routine mat set values stencil. So this is not an arbitrarily sparse matrix, it's something related to a stencil. Okay, so again we iterate over the local domain, and matrix coefficients are dependent on position, so I don't know. Okay, Now here's a strange data type. I think it's kind of a misnomer. Mat stencil is not really a stencil. Stencil contains ijk and the number of the field. So what do? So actually a matrix element is one stencil leg, but it's two mat stencil thingamies, one for the I. So a location ij in a matrix, I comes from a 2 or 3 coordinates in your domain of definition. So it's, if I say I, I'm never sure if it's in the matrix or in the domain. Anyway, so that's why in the text it says row and column. Okay, so you have matrix element sub row column, and the row is constructed from I and j, and so if you have a 5-point stencil, then for each row you have 5 columns. And so for instance, the diagonal element has I, the I is I and the J is J. And the other legs of the stencil, so for instance, row, the row is has I and J. And for instance, the connection to the top row, no, if I, yeah, the connection, stencil connection up is, your column stencil has the same J, but I is -1. Okay, it's kind of hard to phrase this, but I hope you can see sort of what's happening. And so you construct your stencil. So 1 row, 5 columns, and you insert those values. Okay, so here you've again used the grid information to iterate over your physical domain. So it's always good to stay closer to application terms. A matrix is often not a very insightful thing to work with, and doing it this way, you formulate things in terms of your application. Especially if this becomes 3-dimensional, then you're still talking about a row and column in your matrix, but now you relate them to ijk in your physical domain. Okay, and then at some point PETSc got, and this this is very complicated stuff, DMPlex. So there is support for unstructured finite elements. You describe your vertices, edges, faces, interiors, and you have functions for your convection and your diffusion, and it's all very complicated. So I am not going to go into this, and I am calling it a day, I think. Almost. So this is the grid manipulation chapter. I'll just mention that PETSc has nonlinear solvers, Newton with line search, Newton with trust region, and a couple specialized ones. So there is support for nonlinear solvers, and of course in each step they do a linear solver. Yeah. I'll say even less about time stepping methods. Wait a minute, there was a slide. No, there is no. There's no slide about that. I don't think PETSc is terribly sophisticated in time stepping. Euler forward, backward. What's the symmetric one? Crank-Nicholson. If you want to do ODE solving, then PETSc can interface to PVODE, and that's probably a better solution. And then I will mention that PETSc has a whole bunch of profiling and debugging tools. So I briefly used the log summary to get the runtime. It has way more information than that. You can make your own events. Oh, I didn't show you this, but so the log summary gives the time for each PETSc routine. And if you think this is cool and you want it to report on your own routines, then you can make your own events. Let's see, I showed you the check error and set error. I mentioned that PETSc has its own malloc and free, which are pretty great because if you sprinkle check memory calls through your code, then it will try to detect memory corruption, so you don't have to wait for your code to crash. And that is the last slide. Yes. Okay, this is a boatload of material and I've still only touched on a couple % of all possible PETSc routines, but I hope this gave you an idea of what's in PETSc. So we talked a little about general distributed linear algebra. I gave you the mental model of how PETSc works and how you compile it. Vectors, matrices, linear solvers, and that is for many applications the bread and butter. If you have something that is on a Cartesian grid, then you can use the DMDA routines. Parallel data management, sometimes it's useful, so be aware that the vec scatter exists. Beautiful mechanism. And nonlinear time stepping, but take a look at the profiling and debugging. That's often quite useful. Okay, that's it. Any remaining questions? Okay, I hope you've all bookmarked where you can get the lectures book, repository. The repository does not contain the PDFs, it only contains text sources. But the repository does contain all the exercises. If you have an existing implementation of PETSc, meaning you have a code that uses PETSc, what's the best way to optimize solve time? Yeah, it's a matter of experimentation. Iterative linear solvers are a black art. Some people talk about numerical folklore. So if your code is very complicated, you could, for instance, use a PETSc viewer object to dump a matrix to file, and then write a, or use my program, write a short program that loads the matrix and then try out different solvers with it. So that's what I would do. But it's a matter of experimenting. There's a whole bunch of possibilities, so read through my slides. I think I touch on most of the common ones, especially the ones that you get extra from Hyper. They have some cool parallel facility that's not in the standard PETSc ones. So yeah, use KSP view to see what's currently happening in your solver and then try something else. What just happened in chat? Okay, Lauren just posted that machine resource allocations will expire this evening. So if you're, I guess this means if you have a tutorial account and you don't otherwise have budget on Frontera, then you can play until tonight, and then then your temporary allocation will disappear. So I guess this is for. Oh, we don't use training accounts anymore, right? So everyone has a legitimate account, but maybe people only have an allocation for this training.
Right, yeah, that's how we do it.
Okay, yeah. So if you don't have an allocation of your own, then what you're currently using will go away by this evening. And so if you want to play a little more, we have a guaranteed allocation until 4 o'clock. So until then, you'll find it easy to get a couple of IDEV nodes. Okay. Yep, and the video will be posted on TAC's YouTube within a week. Cool. Okay, that's it for me. I don't see any questions appearing, so Lauren, you can shut this down. I will keep looking at.
We have someone typing to you in Slack.
Yes, I'll
thank
keep
you.
Slack.
The tutorial is great.
I saw that. I'll keep the Slack open. Okay, bye everyone.